Welcome to the Webinar Wednesday presentation of From Datasheets to Results, which is on thermal analysis with the SOLIDWORKS Flow Simulation electronics cooling module. I'm Damon Tordini. I'm the product manager for Flow Simulation. So I'll be going through one of the most popular applications for this product, which is performing analysis on some sort of electronics product to check temperature constraints. And I'm going to be focusing on something that we don't talk about a lot, which is when you're getting to the point where you're planning on doing the setup for one of these things, what capabilities there are in the software that let you actually take whatever the real world data is about your product that you might be able to find, and how you actually can put that into the software and make sure that the results you're getting out are accurate. So I'm sure, like many of you out there, the typical SOLIDWORKS user among our kind of customer base is mostly going to have a mechanical design background. That's what my background was. And of course, along the way, I've managed to learn a little bit about circuit boards and components that may go on them. But in many cases, if you're like me, you found yourself in a situation where a product that you might be designing or validating is, of course, going to need to be cooled. But in a lot of cases, a big part of that cooling is going to be something that was already designed into the board itself, or maybe even inside the component. And while we might be trying to look at some mechanical design changes, such as moving fans around or putting a vent in an enclosure or designing a heat sink, in a lot of cases, whether or not the chip can stay at a proper temperature is also dependent on how those internals were designed, or other aspects of, let's say, the layers in the PCB, or cooling devices that we might use that are more sophisticated. So if we want to make sure that we are checking these thermal requirements and we're getting the best mechanical design, we want to make sure that we are capturing those electrical design features as accurately as possible, so that we know if, for example, the chip itself has been designed in a certain way to get the heat out, that we're accounting for that too, in addition to whatever kind of heat sink we might be trying to create, or how we decide to create, let's say, vents or component placement on the circuit board. So we're going to look at how you could use SOLIDWORKS to have an integrated, what we call design validation process, where you can take some of that information from the suppliers of these components and put it into SOLIDWORKS to increase the accuracy of your results. So of course, in the solution portfolio at Hawker Systems, right now we're talking about the simulation family of products. And of course, those are highly integrated with the design tools, which is generally going to be SOLIDWORKS. And so let's think of a case study where we might be using some of these tools. In this case, a compact PC, compact personal computer, where we got really just one main board with some components on it. And in order to kind of simplify things, we've got a single exhaust fan on this case, just trying to get the heat out. And we're cooling those things via heat pipes. And I think we've got a thermoelectric cooler in there. And of course, the chips themselves have been selected for their cooling. So we're going to try to see what changes we might make to the layout of the board to figure out if those components are going to be below their thermal constraint, which in this case, we're going to say is 70 degrees. And of course, in order to make sure that the changes we want to try out, the mechanical design changes we want to try will give us a good conclusion, we need to make sure that we're capturing how that chip's going to behave accurately. So the way we can test these things is specifically going to be with a product called SOLIDWORKS Flow Simulation. That is in the SOLIDWORKS simulation family of tools, meaning it's going to run directly inside SOLIDWORKS on your existing solid models. So of course, there's not going to be any need to export the model or create different versions of it. It uses the existing solid geometry. And specifically, this is what we call a general purpose fluid flow and heat transfer simulation tool, which means it can be used for a lot of different purposes, but the most common one is electronics cooling, as we're going to be looking at here. One of the best parts about this product is that because it runs directly on the SOLIDWORKS model and because the meshing technology is very automated and very robust, in most cases, you're going to be able to take the exact geometry that you've already got, whether that's something you created or if it's got some circuit boards in it that were maybe given to you, and you won't have to modify them in any way before you run your analysis. And once you set up the analysis, you'll be able to start playing around with the design, trying out different changes to see what happens much more rapidly than if you had to sort of outsource it or create special variations of the design just to do CFD. So this is something that any SOLIDWORKS design engineer would be able to take on. Now, of course, if you are designing an electromechanical product, you're going to have a circuit board in it. And in many cases, you might be using a newer product that came onto the market a couple of years ago called SOLIDWORKS PCB, which is, of course, a circuit board layout tool based on Altium Designer. And if you choose to use this tool or something like it, you'll either be collaborating your board layout directly into the SOLIDWORKS 3D model, or you might be importing some other kind of board file like an IDF through CircuitWorks. But the reason this is important is that in different board layout programs, you might be exporting the different levels of detail, the geometry to SOLIDWORKS. You know, there are certain programs out there that would let you export the entire internal design and details of a board, for example, and maybe even the fully detailed internal components on the board. But from our experience, that's pretty rare. In most cases, you're probably going to get something a lot more simplified, which would be like, for example, just a solid block to represent the PCB, and then probably solid components, you know, where each chip, for example, is just maybe an extrude or a couple other simple features. And that's fine because it does help speed up this integrated design process where you could go back and forth between mechanical design and SOLIDWORKS and your board layout. But what that means is if you are bringing in a PCB really with any of these methods, you're probably going to have a somewhat simplified model of the electrical side, because again, that's not something that you would create from scratch in SOLIDWORKS. And so we need a way to represent what those internal details are, just like you're seeing in those board layout images there, in SOLIDWORKS. We're not, probably in most cases, not going to be modeling the internals of a chip or modeling in the solder balls, but we need a way to account for that stuff. Something that is probably a little more typical for what you see would be like in the bottom right image there. Once I bring this board into SOLIDWORKS, which of course you can see the fully detailed version of on the left. For example, those RAM components, the memory chips on the right-hand side of the board, they just become simple blocks. Again, every company's different, but this is what we usually see. This was typical. So how do we account for those details when we've already simplified the model in SOLIDWORKS? Well, the key to this is that SOLIDWORKS Flow Simulation has a special add-on module, and there's actually two of them, and one of them is called the Electronics Cooling Add-on Module, and that has some capabilities specifically for defining the properties of these types of components to make sure that they're being accurately represented from a thermal standpoint when you're going through the analysis. And that way we won't have to spend as much time importing all the internal mechanical details of the component, which we may not even be able to get in some cases. So we'll be going through some of those features in a moment here. First of all, let me pop up the model and show you what this kind of case study example is going to look like. And then we'll go through and look at what the electronics cooling module adds and how we actually could get those properties in there from real world data. So let's open up SOLIDWORKS. And this is just going to be a normal SOLIDWORKS assembly, of course. I'll open up here. So again, we've got sort of a sheet metal enclosure. We've got a single large circuit board with the CPU and a memory controller on there, a couple other things. And we've got some heat pipes connecting those chips to a big heat sink right in front of this exhaust fan. So if we want to analyze what the temperatures in some of those chips would be, of course, we can turn on the flow simulation add-in here by clicking the button from the command manager, and then we would need to create a new simulation. Now the flow simulation add-in, of course, starts with the wizard interface. So even if you've never really done this before or you kind of are rusty at it, most of the time you'll be able to remember pretty quickly how to do it by following the steps in the wizard. So just to give you an idea, we'll go ahead and create a new project right here. I open up the wizard, and the first thing I do, of course, is give it a name, maybe like maximum CPU use. And of course, I would select whatever configuration of the model I want. And in some cases, you might have a fully detailed version of this assembly with all the internal details, but you might also have a simplified version where, again, the components are represented as for simple extrudes or other single bodies, which is, again, what we usually see. So we'll give it a name, make sure we're on the right version of the model. We can throw in our units, for example, SI units, and maybe Celsius for temperature. And then we can choose what physical features we want to include and what actual physical effects are accounted for in the simulation. And so, for example, if we are looking for temperatures inside solid components, of course, that means we need to account for heat conduction. So we'll check the box next to that. If the effect of air rising, for example, on natural convection, was important, we would turn on the gravity checkbox. Although in this case, I've got a big fan on there that's pulling the air, so it's probably not as important. And of course, there are other things I could turn on too, like radiative heat transfer, if this was, let's say, really hot or maybe outside in the sunlight. And I could even do a time-dependent simulation to see how long it actually takes to heat up or how long it takes to cool down once I have turned off the device. We've got our fluids library here. Of course, most of the time we're going to be specifying air in a product like this. In some cases, you might have a water cooling setup, in which case you could also add water to the analysis and define a separate fluid space inside the water line or inside the pump. You'll notice we do have heat pipes in this model here, but we're not going to need to simulate the internal fluid or phase change of the heat pipe because of the ability to just bring in the heat pipe specification from the supplier. So we don't need to simulate those complex physics. We also put in our default solid material. We'll go ahead and just choose an insulator material here, which is just going to have zero conductivity. And then we'll specify the other materials later, like copper. We can put in some wall conditions. We're going to assume smooth walls and no radiative heat transfer. And we'll just use the default ambient conditions, sea level, temperature, and pressure. And so once that's done, we'll have a new project here. And then we can go and specify the rest of the detailed setup conditions. For example, our boundary conditions, which would be where the air is able to, let's say, get in and out of the box. In this case, I've got a vent on the left side of the enclosure over there and one on the bottom. And while those were originally modeled up with the actual detailed slot profile, here they've just been simplified to a simple rectangular cutout. And if we wanted to, there's a way to specify what that hole pattern was so that the airflow is reduced accordingly. But it would be as simple as selecting that face, for example there, and specifying what we would call an environment pressure boundary condition. And that's just going to mean that boundary condition, of course, will allow air to come in or leave the system based on any of the other flow conditions we put in, such as a volume flow rate. We also get a fan here, which is going to be removing the hot air from the system. And of course, we could put in another one of those boundary conditions, like, for example, a fixed volume flow rate. But if you're familiar with fans, you know that the flow rate you actually get from the fan is going to depend on a lot of other factors, particularly if there's anything restricting the flow, like that big heat sink I've got. So if I want to accurately see what flow rate I'm going to get based on, for example, if I move that heat sink around, or if I, let's say, remove some of the fins, I need to put in the actual fan curve. Now, SOLIDWORKS Flow Simulation has a library of some limited fan curves. And if I were to go here and create the fan condition, I'd simply select that face, say it's an outlet fan, and I would need to browse and select the fan that I want to use. And we've got some from Pabst here. So I can go select one of these, and you'll see if I go into the actual engineering database itself, the data that's contained in here is a curve that shows the relationship between the pressure drop across the fan, or pressure rise, and the volume flow rate. So the bigger the pressure difference is, if there's a big restriction in front of the fan, I'm going to have less volume flow rate. So again, if I've already picked my fan and I'm trying to design other stuff like this heat sink, this is a great choice. If you don't know what fan you want yet, you don't have to use this. You can just put in a flow rate, and that might help you decide which fan model that you need to choose down the road. There are also some different solid materials, of course, we might put on, like for example, some of these connectors we could assume are plastic, or maybe the case we want to just assume is steel. And that's just a matter of selecting the components and specifying the material. I can click the cover there, and I've got some predefined materials, like for example, stainless steel 321. So that's all pretty straightforward. Now, of course, if you didn't have the fan curve already in the library, that's something that you could request from the vendor. And again, that's probably on any data sheet you would get for the fan. And it would be a simple matter of typing in those properties, just like I showed you a moment ago. Same thing with solid materials. Got a thermal conductivity and probably a specific heat. Very straightforward. But what about some of these other more sophisticated components on the board? That's when things get a little trickier, and we need to take advantage of the electronics cooling module capabilities to put in more accurate data. I'll give you an example, of course. This CPU right here, if we were to split it up and look at some of the insides, we'd probably find that there's a silicon wafer in there, but there's also going to be some leads on the bottom. Actually, this one might be a BGA, so there might be some solder balls. And there's probably a plastic case on the side, and maybe even a heat spreader on the top, a little piece of aluminum to help get the heat out. If we were to just put a solid material on that chip, the way I just did for the case, I'm going to be pretending that the thermal resistance or thermal conductivity throughout the chip is just the same in all directions. And we can tell right away that that's not, again, a very good assumption, right? We know that the heat is going to get out of that chip to the bottom of it, where the board goes, differently than to the top where this heat pipe is connected. So how do we account for that, or other factors like what the inside of this PCB looks like? Well, that's where these capabilities in the electronics cooling module will come in. The first one I want to look at is something called the PCB generator, PCB layer definition. So if you have a circuit board, which of course is made up of alternating layers of dielectric and conducting material, where you've got traces or ground planes or whatnot, all those internal features, of course, contribute to the heat transfer. And like we said at the beginning, more and more as products get smaller, like the cell phone that's got to have the thinnest case on the planet, we need to account for some of those factors and make sure we're simulating the heat transfer accurately. In many cases, the board itself is really the only thing getting the heat out of these components. So what the PCB generator does is it allows you to type in the actual layer information from that board into the library in Flow Simulation, and then calculates the equivalent thermal properties for you, including how much thermal resistance there is through the board, which might be very high, compared to how much resistance there is in the plane of the board, which may be much lower. So we can put in the number of conducting layers in the board, for example, an 8-layer board. We can put in what the thermal coverage is. For example, a ground plane might be almost all copper, so it might be 80%. Or a simple power trace might be more like 20%. And we can put in the thicknesses of the layers, and of course we would also specify what material they are, whether that's copper or FR4 or something else, if it was the dielectric. And so from all that, the PCB generator calculates the thermal properties. Now, where would we get this information? That's, of course, one of the questions. Now, you might be able to just call up the board layout team, or maybe the company that did it for you, and ask. But if they aren't sure, the best place to look would be in the actual board layout software that they were using. For example, if they were using SOLIDWORKS PCB, there is something called the Layer Stack Manager, which actually lists this same information. It has a table that shows all the layers, whether it's the dielectric or the conducting material, and what the thickness is, and also, of course, what the order is. And so that, combined with also looking at the top-down layout of where the traces are, would help you input what these layers are and what the coverage is of each one. And other board layout programs are going to have this same type of info, whether that's Altium Designer or PADS or any of the others. So for example, in our model here, I've got a little custom 4-layer board that I can put in. And if I just go to the printed circuit board feature, I can go select it from my library, which looks like this. I've got all my material properties in there and then the board definition itself. And when I put that info in, SOLIDWORKS does all the work, calculates the effective thermal conductivity in the different directions, and all I have to do is pick the part. So, no need to do a bunch of math on your own in an Excel spreadsheet. Now, if you wanted to account for more sophisticated circuit board features, like for example, vias underneath one of the chips, which let's say might be all copper going all the way through the board, you could also split that part into a couple other bodies. For example, do a simple rectangular sketch underneath that chip, do a split feature, and then the board would be 2 solids. You could put copper on one of them to represent those vias, and then the rest of the board would still be this printed circuit board feature that we just looked at. Let's look at another example. What about these chips themselves? These are obviously just modeled as a simple extrude feature, so I need a different way to put that information in. That's where another capability of the electronics cooling module comes in, called the Two-Resistor component model. The Two-Resistor component model is what we call a one-dimensional network assembly or network relay, which was created and approved by the JEDEC standard to more accurately give you the junction temperature, in other words, the internal temperature of the actual silicon wafer in the chip, based on some 2 simple numbers which describe what the other materials in the component look like. So rather than just trying to pretend that the whole chip is made of the same thing, we can put in these 2 values, the JB, junction to board resistance, and JC, junction to case resistance, and have a much more accurate picture of how the heat gets down to the board or up to a heat sink. So again, where would we get these values? How do we find theta JC or theta JB or things like that? Well, in most cases, if you pull up a component data sheet, for example, this is a memory controller here. We've got, if you were to look at the document itself, it's of course a pretty long document, but if you did a quick search or scroll down, you'd most likely find a page such as the pin configuration table like you saw down there, and that's got some thermal resistance values right in it. So we've got the 2 values we need in the units that we need, which is going to be temperature per heat power. So degrees Celsius per watt or kelvins per watt, something like that. And all we need to do is find those 2 numbers, and we can put them right into the engineering database in SOLIDWORKS. That's all we need, 2 numbers. And in addition to that, we would need to put in the heat generation rate, what power the chip is running at, but of course that might change depending on the application. These 2 properties generally are going to be the same for a chip, that they'll never change. Sometimes they're described differently. Theta JA, for example, is the thermal resistance to ambient. So if the chip, for example, doesn't mount directly to a board, they might describe it differently. Maybe because it's got some kind of standoff leads. Either way, you can still use the Two-Resistor model for that. So again, I could go into my setup here. I could create a Two-Resistor component. Go find that component from the library, like this one here, this LTC memory controller. I've got those 2 properties in here for the junction to case and junction to board resistance. So you can see, for example, that the heat has a much harder time getting out through the bottom of the chip, right? It's going to flow to the top where the heat spreader is much more easily. And then all I have to do is select the component, and make sure that I've clicked the top face. So that would be the junction to case side. And then I simply put in what heat power it's running at, let's say 2 watts. So again, that's going to give me a much more accurate internal temperature, and I don't have to worry about doing a bunch of math or guesswork in my head to try to approximate that with a material. Another type of component that's commonly used to get the heat out of products like this would be a heat pipe. And as we talked about in reality, heat pipes have some sort of a highly conductive fluid on the inside of them, and they generally work by using two-phase sort of a heat transfer process where the liquid might boil off, recondense, flow back around sort of along the sides of the heat pipe and repeat. And of course, that's a very complex two-phase flow problem with heat transfer as part of it. In fact, the condensation and evaporation part of that is really beyond the capabilities of flow simulation and most other CFD tools. So we need an easier way to represent this heat transfer through the heat pipe. And the good news is that heat pipe manufacturers usually have a value that can describe how effective it is, much more simply than that. We don't need to go back to the drawing board and try to re-simulate the product that they already came up with. And so if you look at a heat pipe data sheet, for example, one from Avid Thermocore here, they often have a thermal performance chart on them or specification, which generally shows how much of a temperature difference from the start to end of the heat pipe you'll see or you can handle for a given amount of heat power. So for example, depending on which diameter you choose here, you might see a delta T or temperature difference of 12 degrees for a power input of 25 watts. And with some simple math, because all we're looking for here is kelvins per watt or degrees Celsius per watt, we can punch that value in. For example, 12 divided by 24 is 0.5. So again, all we need to do in the software is create a heat pipe feature, put in that value, 0.5, and you select the components as well as the faces where you want to assume the actual heat pipe is being located. And of course, I could pick it from the tree and use select other to grab all the other faces at the inlet and outlet of the heat pipe. So that'll simply transfer the appropriate amount of heat from the chip, in this case, right to that heat sink. And I don't have to worry about trying to fake it with a material or changing what this effective thermal resistance is just because I reposition the heat sink, which is what would happen if I tried to assume it was just pure copper. Brett had a quick question, by the way, which I'll go back to and address. Brett asked if there is more than one body, is the heat spread out among all of them for the two-resistor component? And the answer to that is actually the two-resistor component model does need to be created on a single body. So if you had started to try to model the details of the chip, the inner details, what you'd want to do is a simple combine feature. Combine them into one solid body, and then the two-resistor component model will work. What it's really doing is it's sort of ignoring the actual geometry itself and replacing that with this sort of network assembly model we talked about here. So it's going to just assume a vertical thermal resistance to the inside of the chip, but because it accurately calculates it based on those resistance values from top to bottom, it's going to be much better than just assuming the material. All right, so we've got some of these different types of components in there. Now, there of course may be other things that we need to add to this setup. And if we switch over to the finished one, you can see some examples of that. Of course, we've got our fan. We've got a different kind of heat source here, which is just a volumetric one. That would be kind of the traditional or less accurate way to do it if you couldn't find those two resistor components. And so in some cases that's necessary. We've got some heat pipes. We've got some two resistor components. We even have what we call a thermoelectric cooler, which if you're familiar with is sort of an active cooling device that has some current going into it to help transfer the heat from one side to the other. And in all of these cases, of course, we can select the values that we want to use by just picking an existing item from the library. So we might have a thermoelectric cooler that we already created in our engineering database with the right properties. The good news is, whether it's a TEC or just even a simple solid material, the electronics cooling module comes with a much larger library of those items. So for example, if we're talking about a simple solid material to represent a chip, two resistor components themselves, sample circuit boards, fans from about a dozen different manufacturers, and even thermal pads or thermal pastes, all of those are included in this expanded library. There's probably a couple hundred items overall. So it also, even if you, for example, want to use some of the more traditional ways of setting this up, it's going to provide you a lot larger list of options to choose from, and maybe give you a better idea of what kind of properties you should be expecting from a custom component that you want to put in. And if you didn't know, all of these properties in the library that you can create or just use from the default, they can also be saved directly into the part file themselves in SOLIDWORKS, which means if you've got a chip that you regularly use, when you bring it into your assembly and then create a flow simulation project, that two resistor component or other model can be immediately imported. So when all's said and done, if we went back to our analysis here, again, we've got our materials put in, we've got our exhaust fan and all the other components on the board. We could run the simulation, and of course that would give us the airflow patterns, the temperatures in those chips, and we'd be able to test whether or not we're meeting that specification. If we just hit the run button here, this is going to generate the mesh and then begin the analysis. And if we take a quick look at what the solver window looks like, what we'll see is, of course, the mesher is automatically deciding how to refine itself so that we get the detail of those fins, or maybe even the trace. And you, of course, have the ability to manually refine the mesh on those parts if you wanted to, but the default settings usually do a good job of capturing them anyway. And in this case, we're doing a fairly coarse mesh. We didn't add in a lot of manual refinement. So it's only going to take maybe a minute here to solve. But what we're going to see as the calculation starts up are the values of what we call goals, which are basically like sensors measuring those temperatures that in the chips, just like we talked about. Of course, we're trying to figure out if we are past our thermal limit or not, which in this case was 70 degrees. And what the simulation is doing here is it's just calculating how the airflow sort of passes through the system, what the airflow patterns look like, of course, how easily it's getting to the fan and out through the box. And the simulation is essentially going to keep looping those airflow patterns until it hits what we call convergence. And what convergence means is just that we've found the steady state behavior of this product. The airflow patterns are all constant, the temperatures are no longer changing, and this is going to mimic running the device for a long period of time until everything stabilizes. And so once you start to see all of those little charts in the solver window level off, you'll know that we're getting close to that convergence. And of course, when it happens, all those little progress bars will light up green and the solver will finish. So the solver completed, and now I can go see the result. I can find out if my temperatures were too high, or what my airflow patterns look like. And of course, there's a large variety of result plots that can visually show you what's going on in your analysis. For example, a cut plot, which is essentially a section view showing you any kind of result you may want, such as temperature or velocity. Here we've got it enabled with the streamlines so that I can see the airflow patterns and sort of where the air is getting to where I want it to go and where it's being blocked. And I could also see things like the mesh and find out how much refinement did the mesher do. For in this case, you can see that it subdivided the mesh in that heatsink to make sure it was calculating the air through the fins properly. We can show a lot of other things like, for example, surface temperatures on the components, and even the three-dimensional airflow patterns inside the box. Now, of course, the question is, once we've done this kind of analysis and we've evaluated the baseline design, what can we do to improve it? And of course, that's the entire point of SOLIDWORKS Flow Simulation. Because we're integrated into the SOLIDWORKS CAD tool, at this point, I can simply make a change, run the analysis again, and see what happens. And if I look at some of my visual plots, like for example, the flow trajectories here, I might be able to qualitatively just kind of make a guess of, what do I want to try? What might be better? In this case, because of the location of that RAM chip, the SODIMM under there, a lot of the air is getting sort of diverted over into the corner and it's getting stuck. So what if I move that chip over, see if I can open up that intake vent and get the air going around the other way where I want it? Well, all I need to do is either just change the mate or change the dimension, or what I might want to do is create a configuration first before I make that change so that I can have both versions side by side. So here I've got another configuration of the assembly called Flow Simulation Rev B. I'll just go switch to that one. And there you can see my memory chip has been moved. And then all I need to do is hit run, analyze this same calculation again. All the setup conditions are exactly the same as before. I didn't need to redo them just because I changed the geometry. Now, if I were to run this simulation, of course, I get another set of results. And at that point, if I wanted to look at these side by side and figure out which one's better, I could use something called the compare tool to do that. There's a compare tool that you can click in the drop-down. You can select any of the different analyses that you created in this assembly and look at all the different plots, like the goal plot or the cut plot. And those results will load up and be displayed side by side in this menu on the bottom half of the screen there. So for example, if I look at my temperatures inside the components, you can see there, for example, I've got one called LT3029 max temperature. That would be the junction temperature inside the two-resistor component. You can see that it went down a little bit, not a huge change, but moving that RAM chip just had enough of an effect on the airflow patterns to reduce it. And obviously, in a lot of cases, we're going to be talking about changes of maybe only a couple degrees when we're looking at repositioning board components or maybe changing the heat sink. And so obviously, if we've got a margin that small, we want to make sure we're capturing what that internal temperature is as accurately as possible. And if we were assuming that that chip was just made of pure silicon, for example, we would be a little off base and probably not in the range of accuracy that we would really need. So the purpose of all of these features is to make sure that the comparisons we want to try out in SOLIDWORKS are giving us the right conclusion. We can see, of course, in this case, just from the airflow patterns, that that change was qualitatively a good choice. But we may also want to make sure if we really are underneath the thermal constraint that has been given to us by the project manager. And so all these component properties that you get direct from the supplier data sheet will help you have confidence in those results and know that you really will see that kind of a conclusion when you build this, test it, and submit it for qualification. Other types of problems that you could examine with this kind of a tool would be, for example, mechanical design aspects of the enclosure, like how many fans do I need, or where should I put the fan if I only want one or two of them. Of course, we all want to make the products more reliable out there, so fewer fans is better, especially if noise is a concern. And again, maybe the component properties themselves are not changing. It's probably the same chip, but that way we know that we have less error and more confidence in that chip temperature based on whatever we change on the mechanical side. And we know that this is a valid solution because we've got a pretty large community of users that have purchased Flow Simulation and regularly use it for this type of a process. Electronics cooling, again, is one of the most common ones. So aside from industrial or energy sector, we've got consumer products like IOSafe and customized high-tech electronic groups like Polyrack. So if you are interested in getting some more information about who is using Flow Simulation or how, or if it will work right for you, of course, there's plenty of information on our website and educational resources. But of course, as always, you can reach out to your local account manager, or you can call the technical support line if you've got any technical questions on your existing SOLIDWORKS products or whether it can do some of the capabilities that you're looking for. With that, thanks for joining, and we'll see you next time. And before we end here, it does look like we've got some questions. I just want to wrap up. So Brett, I think I answered this a little bit earlier on in the presentation, but just to clarify, again, if you have a two-resistor component, you want to make sure that it's modeled as only one body, and that way it'll let you select it. Now you can have more than one face. The selection box will allow you to pick multiple faces to represent the top side or case side of the component. If, for example, there's different features on there, but the part itself should be a single body. So hopefully that makes sense. Again, if you had modeled the chip in more detail than that, at a certain point you might decide that you just want to model the internals of the chip and then put the actual materials on each of those bodies. But most of the time, that's not what we see done. So if the chip has been modeled as a single solid, that two-resistor component is a much more accurate way to represent it. Marco asked, was this done as an internal or external analysis? Marco, this was an internal analysis. So the box was sealed, and which is why I put the boundary conditions on the model. We go back, I can show you here. We've got those vent openings sealed off with lids. I could have certainly done it as an external analysis instead though, right? So we could have done an external analysis which includes some of the airflow around the box. And in that case, we would have wanted to actually leave the vents themselves modeled into the case, whether that was a slot pattern or let's say a hole perforation or whatever. So an external analysis will definitely take longer to solve because of that, but it will be a little faster to set up because you won't have to do the lids, and it will be more accurate too. So it's your choice. By the way, that's a concept that we cover in a lot of detail in the electronics cooling training class that we teach for flow simulation. It's a half-day online class for people that have already used flow simulation a little bit and want to get into electronics cooling specifically. If you go to hawkridgesys.com, you can look at the training page and find out what the course description is and when it's coming up next on the calendar. All right. If anybody else has any questions, let me know. Otherwise, we'll be wrapping up in a minute here. And I want to just thank you all again for your attention, and I hope it was useful for you. And again, reach out to us if you have any further questions or applications, or you want to see if flow simulation is right for you.